All right, everyone. Thank you for attending. Try to see what I'm trying to do here. Basically, as I had promised the people in my class who were at the last couple lectures, that I would try to put something down in a film. It's not going to be a very lengthy presentation, but hopefully a halfway decent summary of some topics regarding energy considerations, regarding momentum considerations, and more specifically regarding the rocket problem. So let's, those who have been in the class quite a bit, attending in person, and it's always a good idea to do so. I mean, your grades, however people want to do this, you're not graded on attendance, but attendance is a good idea. So I would suggest that in any class that you ever take. But at least we have to know what's going on. At the very least, guys, when you're doing these exams and these homework assignments, be very aware of the PDF solutions that are present for you on Canvas. There are many PDFs on Canvas. They are probably the most time-efficient way to study various things and also just get notes on various topics that are going on and be able to approach doing a homework assignment and to be able to approach doing an exam. For your homework assignments and for your exams, the PDFs and the book are probably the most time-efficient way to go. There are many films out there that I tried to put together. Most of the films are of really good quality, at least audiovisual wise. Some are not of the greatest quality. There were just certain things that just weren't known at the time when we were trying to do various things. I guess you live and learn, I guess. So, but the professionals with whom I've dealt that have done the very high quality films have done a tremendous job, and been some people who have helped in that regard. So the audiovisual quality should be pretty decent when you're looking at these films. Probably the most time-efficient way to proceed are reading the book, reading the problems in the book, and then looking at my notes and at my solutions for various problems that are in the book to help you do the homework assignments and to help you do the exams. Probably the most time-efficient way to proceed is that. The PDF solutions for practice lecture problems and for practice homework problems, those PDF solutions are probably the most time-efficient way to proceed. Usually a lot faster than any kind of film. Okay. So what I had done in some of the books that I'm looking at, there is mechanics that uses calculus. Some courses use calculus. Some courses do not use calculus. So this is from a book that does not, I believe was a non-calculus version of the book. Let me just see to be sure. Almost certain of it, but let me just, and then I just kind of manipulated it a little bit here to see what we could say about it. Right, this was from a non-calc version of a book from the Serway book, Serway and Buell, 11th edition, Serway and Buell, 11th edition college physics, and then the calc version of this course is for this particular school. We're using the Katz book, Physics for Scientists and Engineers, Volume 1. So the Katz book is calculus treatment, and the Serway and Buell book is non-calc treatment. I've gotten this from the non-calc treatment of a book that has a non-calculus treatment. There is a table. The table can be very, very large. The ropes can be very, very large. And all the ropes are massless, have no mass, and all the pulleys have no mass either, and there's no friction associated with them. The only place that there is friction is on the tabletop where mass M2 lies, and that's the only place we have friction. And we can make, we could set this whole process in motion. There are masses 1, 2, and 3, and there's a coefficient of kinetic friction, mu sub k, associated with m sub 2. And the frictional force will oppose any kind of motion that will take place. M1 is 4 kilograms. Mu sub k is 0.35, M1 is 4 kilograms, M2 is 1 kilogram, M3 is 2 kilograms. If you're holding all of this up somehow, or two people are holding it together, maybe it's a very, very, very large table, but all that I said applies. The ropes are massless, the pulleys are massless, pulleys are frictionless as well, and the only place that there is friction is on the tabletop. Basically, we set up a situation when we talked about force considerations that M1G is going to pull the hardest, and basically M1G is going to set everybody in motion, so this whole thing ends up going counterclockwise. There will be an acceleration upward here associated with the smaller mass, the much smaller mass, M3. Acceleration upward here. It'll accelerate upward when you let the whole system go and just go into motion by virtue of the fact that if there's an unbalanced force, this is going to drive it more than anything else, M1G. And so M3 goes up at acceleration A, M2 goes over at acceleration A, and M1G, so M3 goes up at acceleration A, M2 goes over to the left at acceleration A, and M1 goes down at acceleration A. Everything's going counterclockwise. This is kind of the engine that made it happen. It wants to go straight down. There is a tension that will oppose that. Newton's consideration, Newton's third law, we have T1 and T1 right here. Same process here. This tension will be stronger than M3G. Therefore, the motion will go up that way. Newton's third law, T2 here, T2 there. T1 right here is not as strong as M1G, so it's going to come down. However, T1 is more than T2 because this ends up going that way, because this ends up going down. They're all connected with one another. Counterclockwise for all the motion to take place. Scenario 1 or location 1, general location 1, general location 2, and general location 3, these equations apply regarding force. When you solve for A, you're adding all the left hand, these three equations are three equations indeed. If you add all the left-hand sides, that sum will be equal to the sum of all the right-hand sides. That'll be this. Do some mathematical manipulation, you get to here, solve for A, you get this. When you plug in all the values, you get 2.31 meters per second per second. What we've been saying is, well, look, let's talk a little bit. This is force considerations. If you were going to use energy considerations, there's a number of ways you can look at all this. There's a number of ways you can look at this. But I'll tell you what, it's as simple as that. I mean, all these different ways to look at the energy considerations all essentially are the same thing. There's just a little different ordering of the quantities. You're putting them on different sides of an equation than maybe you did earlier. It's not really the same arrangement, but actually it's the same equation. It's just things have been put in different places. So that's not a big deal. Well, I'll tell you what I'm going to do. If you look at energy considerations, what goes on here is this whole thing gets set into motion. And it's going to stay in motion until it stops somehow. Let's say it's a very big table, long ropes, massless ropes, no mass to the ropes, but this thing can fall for quite a bit. What's going to drive the whole process from happening? What's going to drive the whole process to make it happen, rather, I'm sorry. This is M1G pulling straight down. This M1G is so strong that it'll come down, so to speak, if you give it anthropomorphic qualities, I guess. This is M1G. If you fall H, M1G falling down H is a force of M1G. It's a force of M1G applied over a distance H. M1GH is the work that M1 will do. The work that M1 will do is M1G. When it does that work, we got to balance everything out. Well, M1G does a lot of work. M1G going through a distance H is M1GH. And I'm just jumping from here to here. So let's see how that actually plays out. Well, before I even go there. If you were to take M1G, move it through a distance H, that's M1GH of work. Now, that work that was accomplished by M1G, namely M1GH, where do we account for everything that's going on in here? Well, there's a number of ways to do this, and let me just try to figure out a good way to say it. I guess I'll go, there's a number of ways I can say it. I'm going to say that this M1GH of work that's done here goes to a number of places. What are they? Well, M2 is going to get dragged across also a distance h. If this M1G exerted a force over a distance h, this M2 got moved over that same distance h, as this guy got picked up over that same distance h. Well, if it got moved over a distance h, the force mu sub k M2G times h is the work that was done on this guy to overcome friction. In addition to that, this M3G force is, this weight is picked up a distance h. So M3GH potential energy is gained. Mu sub k M2GH work is done over here, all with this guy falling down. In addition to that, everybody's moving at a speed v. So what happens is all three masses, M1, M2, and M3, are moving at a speed v. Their kinetic energy is 1/2 times the total mass, the sum of these, times v squared. That kinetic energy is equal to what MGH did minus the fact that frictional work was done, so that got put into it, and you picked this thing up and gave it more potential energy. So if you take away the frictional work that you had to do from M1GH, and also take away the fact that you're picking up M3GH, if you take away mu sub k M2GH, and if you take away M3GH from this one doing the big work, you take those away, what's left over is the kinetic energy. And you can solve for that. You can get a V, and you can do some of the manipulations that I've shown in the past of how once you get what V is, you can come back and say, well, let me use H equals this. I can, if I already know what H is, I can find what V is. Or in other words, I could, at this point, you started with initial velocity of 0, then you got this. Well, I just call it, the VF, I'll call V. V squared over 2A equals H. If you multiply by 2A on each side, V squared equals 2AH. And you can kind of figure out what's going on that way. If you know the acceleration, you multiply, if you know the acceleration, you know how far it fell, and you multiply by 2, you get V squared. If you square root both sides, you get what V is. You can keep manipulating, and you can solve for A. You can do a whole lot. Here's another way you can kind of do it. As we see up here, guys, this top one in red, as you see this right here, if you saw the equation we solved here, if you multiply by H, you just say, well, this is force considerations. Why don't you multiply each side of the equation by H? That just means this is a force multiplied by H, you got work that's been done. Multiply by H, multiply by H, multiply by H, multiply by H on each side, you end up getting force times distance, which is work. If you multiply, these are force considerations right here, and if you multiply by, these are force considerations, forces involved. If you multiply by H on each side, you've got energy considerations. That's this. This is cutting us back to what I was saying earlier in the discussion. M1GH is the work that is being done by the largest mass that is present, by the largest weight that is present. The mass is M1, the largest mass is M1, and the largest weight is M1G. M1G is going through M1G is a force going through a distance. That's work. M1G times H is the work that the large weight does. That work, which the large weight does, take away the this is the major part of this large mass right here. Large mass times g, this large weight over a distance h, does a lot of work. Well, where does that work go? Well, all that work that's being done, you're going to lose some of that work. Some of that work is going to go into overcoming friction, and some of that work is going to go into picking up M3G. So you're picking up M3, so you're picking up a weight called M3G. You're picking up M3G. So from this guy, you're picking up M3G, a distance h, and you're fighting friction, this, mu sub k M2G, over a distance h. You're fighting friction and you're picking something up. Those two things get, these two amounts of quantity, this work that has to be done, is taken away from this big amount of work. So this big amount of work accomplishes overcoming friction and picking something up. And whatever's left over is right here. Well, this right here, H, if you look at this equation from the old kinematics, and if VI is equal to 0, then you get this. We'll just call the VF V. We got this right here, guys. H equals V squared over 2A. H is V squared over 2A. The A's cancel. The A's cancel. You got a half that I'll put right here. You got a V squared right here. What happens is the large mass, which associated with the gravitational field is a large weight, or at least relatively large weight, that relatively large weight going down does this much work. True. Of all that work that is being done, some of this work that is being done is used to overcome friction, and other of what's in here is used to overcome picking something up. From this work, not entirely, but from this work, some of this large amount of work that's done is needed to overcome friction, and it's needed to pick up M3 through the gravitational field G. So frictional work is done, and you're giving M3 potential energy. Frictional work is done, and you're giving this one potential energy by lifting it up. The frictional work done, and what you're doing by giving something potential energy. You acquired potential energy, and you did frictional work. That amount of work is taken away from here. Whatever is left over is the motion that's taking place, and that's the kinetic energy that's in there. Now, I did this a little different detail when I did this in person in both my calc version of a class, in both my calc version class and in my non-calc version class, both regarding mechanics, Newtonian mechanics. But this is some of what goes on here. This can certainly be derived. If you go from here, if you go right from the beginning, guys, right here and say, okay, let me deal with this, and let me solve for V squared. Once you solve for V squared, you can get the square root of V, and you end up once you solve for V squared, you can get the square root of V squared and get what V is. Or you can leave V squared as is and solve this. Say, okay, I'm looking at this right here. Let me multiply by A on each side and divide by H. Let me multiply by A on each side and divide by H. V squared over 2H. And that's going to give you the same acceleration as this. It doesn't matter which H you're using. If it's a huge enough table, that H could be 10 kilometers, or it could be 10 centimeters. It doesn't matter. The mathematics will work out in such a way. You'll have, the V squared, if H is 10,000, it's an awfully huge table, obviously, guys, but let's just do it for the thought experiment. If H is 10,000 meters, V squared is a very big number. If H is 1/10 of a meter rather than 10,000 meters, just 1/10 of a meter, V squared is going to be really small. So if H is 10,000 meters, V squared is huge. If H is 1/10 of a meter, V squared is small, but the ratio is always going to be A, and it's always going to come out to this. So it's some pretty fascinating mathematics in that regard. So let's go a little further, guys. Let's talk a bit more. Let's talk about momentum a little bit, and then kind of bring the rocket problem into play, and we'll kind of take it from there. All right, so get rid of some of this stuff. And again, you'll see this, those of you who have me as a teacher at this school, you'll be able to look at the solutions that I have there, especially for the non-calc version of the course, because we're using the non-calc book from which I got this. The other stuff is something I more or less figured we could look at it kind of our own way. It's not something they explicitly go into in the problem, but it's just nice to see it. You can sort of, the teacher, any teacher, in this case it was me, can sort of wing it and bring energy considerations into any problem like this. Okay, so you should have in Canvas and in the PDF documents a lot of this documentation or very similar type documentation. Okay, so all right, guys. There's a good amount of stuff that can get talked about. Like as we always say, it's impossible to cover everything that you like, at least in terms of an in-person lecture, or near impossible to do it. Depends. I guess it depends what's being taught and to what extent something's being taught. But if there's a tremendous amount of material, I mean, some of the material that you can see and that I've mentioned to people, some of this material you can see it. You can look at it. I mean, there's material that can be posted for someone's to help students and for personal enrichment and things like this. All the materials together might take 2 years to look at if you want to look at them in a very rigorous manner. Well, you don't really have to do that. You have to do, again, looking at the PDF documents, the PDF solutions to many of the major problems, and the book should be good enough, and it should be pretty reasonable. If you want to look at everything that's documented, that I try to document, it's an endeavor that could literally take, I think it's realistic to say it could literally take 2 years if you really wanted to look at it very rigorously. I wish we had more time to do this this sort of work, but we got to try to make it reasonable. To make it reasonable is you don't have to look at everything, but you got to look at the main things. You want to look at the PDF documents, the solutions for the practice homework problems and the practice lecture problems, and look at the book, and I think we're going to be okay. They talk about, it's very frequently talked about, you talk about momentum. Now, we do talk about energy being conserved, linear momentum being conserved, and angular momentum being conserved. Well, as far as the linear momentum is concerned, guys, linear momentum is mass times the velocity vector. Sometimes we throw the vector notation out the window without ever forgetting that it's always there in the most technical sense. Acceleration is always a vector. Velocity is always a vector. Force is always a vector. Momentum, linear momentum is always a vector. Angular momentum is always a vector. You've got to always, it's there when you kind of make things a little bit easier to look at. You're never forgetting you're dealing with vector quantities at one point or another. Very important. Momentum is mass times velocity. As far as just let's just go in a straight line and just say, okay, if something's going in a straight line, let's talk about it. The magnitude of the momentum, at least, is mass times velocity. Mass times the magnitude of velocity. Well, you guys remember, we also talked about the force vector being this, right? Well, I'll tell you what. Let's kind of play the game here a little bit. You've seen me write this so many times, right on the bottom there. Force equals mass times acceleration. We got to talk a little bit. Is it true, for example? Let's talk. for the force isn't acceleration, the change in velocity over time. Delta t, or how do we want to utilize the language here, guys? How do we want to talk? Okay, so we got this. If this is the case, is it true if you take m and distribute it on the top, you got this? Wait a minute now. I mean, m times v, m times v is momentum. M times v is momentum. One's final momentum, one's initial momentum. This is the change in momentum. Force is delta p over delta t. In the strictest sense, we're talking about vectors. If you're going to go through the calculus version of this, the deltas become d's, and you're talking about this. So this right here, let's kind of lose the, multiply by delta t on each side, you got F delta t. F times delta t is a special quantity known as the impulse. If there's a great force that you exert over a long period of time, you are going to change the momentum of something very substantially. If there's a small force, and you only exert it for a short period of time, so to speak, small times small is still small. And it's not really a great change in momentum. So, but it should be pretty straightforward. I mean, as the interpretation goes. This they call impulse. Impulse equals the change in momentum. So that's that. There are instances guys, where, I mean, there's collisions that take place. Let's talk about collisions taking place in one-dimensional space. They collide, they come straight at each other, they collide, they bounce off each other, and they go back to where they came from at various speeds, but they go back to where they came from on the exact same lines in which they came coming in. They're coming at each other on one particular line of motion, and when they collide, they leave, and they go back to where they came from in various ways along that same line of motion. So it's just one straight line, and that straight line doesn't change when all this is taking place. That's the case. What kind of, and something they call these collisions perfectly elastic collisions. I got to let you know something, and I already kind of did let you know something. Energy is always conserved, but you got to be careful with that. Energy comes in all kinds of forms. If I look at all kinds of forms of energy that are present, energy is always conserved. Energy is always conserved. Linear momentum, pi vector equals pf vector, is always conserved as well. Linear momentum is always conserved. Angular momentum is always conserved, period. Now, there is special instances where even kinetic energy is conserved. Kinetic energy is not necessarily conserved in any particular collision. In certain special cases, in perfectly elastic collisions, kinetic energy is conserved. But if it's a collision where two cars collide and they stick together, that kind of kinetic energy, the kinetic energy is not conserved. The kinetic energy that was initially present in the system is not the same as the kinetic energy after the collision. But if two, billiard balls collide they're constructed in such a way, let's say hypothetically, that kinetic energy is conserved, kinetic energy and momentum are conserved in those instances. Momentum is always conserved. It doesn't matter what kind of collision happens. Whether it's a perfectly inelastic collision, they stick together, or a collision where they don't stick together, but it's not a perfectly elastic collision, or if it's a perfectly elastic collision where the kinetic energy initially present equals the kinetic energy after. The kinetic energy initially present equals the kinetic energy after the collision. So these are called perfectly elastic collisions. That kinetic energy is not always conserved. Energy, you say, wait a minute, energy is always conserved. I did say energy is always conserved. Energy does not mean kinetic energy. It means kinetic energy, potential energy. It means all kinds of different energy that can be accounted for, and energy is always conserved. Absolutely, that's true. Energy is always conserved, linear momentum is always conserved, and angular momentum is always conserved. Energy is always conserved, energy is always conserved, linear momentum is always conserved, and angular momentum is always conserved. But kinetic energy conserved doesn't always happen. When it does, the collision is called perfectly elastic. The collision is called perfectly elastic. Momentum is always conserved. Nobody's debating that. It doesn't matter if it's perfectly elastic or not. Any kind of collision, they stick together, they fly apart, but it's not perfectly elastic, or they are perfectly elastic. Or they stick together and there's no way that's perfectly elastic. Momentum is always conserved. But if it's perfectly elastic, this will happen. Well, in that special case, I guess there's some interesting conclusions that can be drawn. So, let's have a look. Okay, so let's see what we can say here, guys. If kinetic energy is conserved, if two of those billiard balls collide on a straight line and they leave on that same straight line, we're talking about mass m1 going at initial velocity v1i, having that much kinetic energy, mass m2, the second one, going at v2i, and this is the kinetic energy present there. And at the end of that, m1 v1f, its final kinetic energy, 1/2 m1 v1f squared plus 1/2 m2 v2f squared. This kinetic energy and that kinetic energy added together, this kinetic energy and that kinetic energy added together equals this kinetic energy and that kinetic energy added together. Then there's momentum. m1 v1i plus m2 v2i equals m1 v1f plus m2 v2f. Yeah, it's a little bit of an alphabet soup, you guys. Well, basically, take the v1i velocity of m1, take the v1 velocity of m1, square it, multiply it by m1, multiply it by half. 1/2 mv squared is the kinetic energy. Take the kinetic energy of this particle and add it with the kinetic energy of that particle in the initial circumstances that are present. Initial circumstances, find the initial kinetic energy for m1, the initial kinetic energy for m2. Then find the final kinetic energy for m1, find the final kinetic energy for m2. You add the two final kinetic energies, they will equal the sum of the two initial kinetic energies. That's only in a perfectly elastic collision, you guys. This will only happen in a perfectly elastic collision. Energy is always conserved, but kinetic energy is not always conserved. It's only conserved in a perfectly elastic collision, like right here. What you can do here gets a little on the messy side, but you can do it. Take this guy right here, this 1/2, multiply by 2 all the way across, and get the m1, this guy over here, get it over there. And take the m2, get it over there. So let's subtract m1 v1f squared, subtract m1 v1f squared on each side, get it over there, and take m2 v2i squared, subtract that on each side, and it should be pretty interesting what happens. All right, let's multiply the top across by 2. Multiply the top across by 2. Subtract m1 v1f squared on each side. Subtract m2 v2i squared on each side. And let's see what happens. We end up getting, well, you got the m1s over to one side, and you end up getting v1i squared minus v1f squared. We'll get to that. And on the other side of that, we get m2, you get v2f squared minus v2i squared. Okay, so you multiplied the top equation. Here's 1, here's 2. You multiplied the top equation by 2, and then then subtracted m1 v1f squared on each side, and subtracted m2 v2i squared on each side. We got this. Do something similar over here. Subtract m2 v2i on each side. Subtract m1 v1f on each side. M1 v1f. They kind of look a little similar. Here you got m2, and you got all the m1s over there. You got all the m2s over here. M2 v2f minus v2i. Interesting. Maybe shouldn't have written 1 and 2 on this one. I'll write Roman numeral 1, Roman numeral 2. Let's see what we got, guys. Tell you what, if equation Roman numeral 1, if we have equation Roman numeral 1 right here, and equation Roman numeral 2 right here, if this equals that, and this equals that, then this divided by this is the same as that divided by that. We'll take this divided by this, and you end up getting, let's have a look here. Yeah, right. Over and the other one is v2f squared, v2i squared. We got this. Well, these right here, you guys, what happens is v1i squared minus v1f squared is a difference of 2 squares. It's v1i plus v1f, v1i minus v1f. It's a difference of 2 squares. The other one too. v2f squared, v2i squared is v2f, v2i, atom, v2f minus v2i. So, yeah, I mean, that's called the difference of 2 squares. That comes from this phenomenon. A squared minus b squared equals the quantity a plus b times the quantity a minus b. Doesn't matter the order you do it. So to make a long story short, these cancel, and you end up getting, as we said, I just told you what this one was, and I just told you what that one was. If you put them in those places, look at them. The v1i minus v1f is going to cancel. You got v1i plus v1f. This is v2f plus v2i, v2f minus v2i. you got these right here, the V2F minus V2I and V2F minus V2I. The V2F minus V2I cancels into here, out of here, and you got that. Just like the V1I minus V1F cancels into here, and you got V1I plus V1F. So at the end of the day, you guys, you got V2F plus V2I. And that's a pretty important conclusion for this special case. What does that mean? That means the sum, it helps us solve a lot of equations that involve perfectly elastic collisions. This is only true. This is only true for perfectly elastic collisions, you guys. Here, signs matter. You got to use plus or minus because we are dealing with vector quantities. At the end of the day, guys, acceleration's a vector, force is a vector, momentum is a vector, whether it's linear momentum or angular momentum, it's a vector. Velocity is a vector, et cetera, et cetera. So velocity is a vector, so you got to use the plus or minus here. If you keep it in mind, the plus or minus, and whatever else could be happening here, guys, we're talking about a situation where the sum of the initial and final velocity of the first particle is equal to the sum of the initial and final velocity of the second particle if it's a perfectly elastic collision. If it's a perfectly elastic collision. So that's that. So let's talk about the rocket problem a little bit, guys, and we'll kind of call it a day on that. And I don't want to spend a tremendous amount of time on this. I want people at least to have a little bit of time to view this. If you've seen some of my other videos, they can get pretty long. They're there for you. How much time do you have? They're there for you. I'd rather have them in one place, have them be very long, and then you can jump around within the particular video rather than try to make heads or tails out of videos in many different places. So it's kind of a judgment call. But you can look at some of the longer videos if you wish. A lot of this stuff is covered elsewhere. There's a lot of material covered in a number of places. Let's talk about, let's get a halfway decent look at the rocket problem. Get some pretty interesting conclusions. You see it from a calculus perspective and from a non-calculus perspective as well, depending on the book you're looking at. But let's take a look at it. So we're looking at all this stuff. I guess I could leave that up there. Well, momentum is conserved. Whether it's linear momentum or angular, momentum is conserved. Let's talk about linear momentum. Let's talk about a rocket that's standing still in outer space. And then the engines fire, and exhaust goes one direction, and the rocket goes exactly the opposite direction. That's a manifestation of Newton's third law, and it's also a manifestation of momentum being conserved. If I were on a raft that could hover, let's say it was like some kind of hovercraft or something, some kind of very modern sort of craft, a flying car or whatever it may be, and I'm at least just standing on it, and I have a tremendous number of bowling balls that are right there at my disposal, and I just start throwing the bowling balls over on one side. I start throwing them as you're looking at me. I guess that'd be to your right. If I start throwing them to my left, but to your right, if I start throwing them to your right, the fact that I've thrown the bowling ball, I am pushing against the ball, and that means myself and the hovercraft are going to go in the opposite direction. And that's exactly how a rocket works, guys. It's as simple as that. I pick up the bowling ball. Everybody's stationary, and then I take the bowling ball, and I throw it. I throw it hard. and I throw it, and then I'm throwing the bowling ball, it's leaving, but I'm also pushing against the bowling ball. I'm pushing myself off the bowling ball, go that way. The more bowling balls I can pick up in a given period of time, and the more massive that they are, and the faster that I can throw them, and the frequency at which I'm picking up the bowling balls matters as well. So you talk about the mass of what I'm throwing, how fast I'm throwing it, and how much of it that I'm throwing. If each bowling ball is 5 kilograms, if I can do 5 kilograms once every 10 seconds, and I can throw it pretty hard, I can throw it 10 meters per second, let's say. Unlikely, but let's say I could, or some machine could for me. If I throw it at 10 meters per second, if I can throw it at 10 meters per second, it's a 5 kilogram ball, I can do it once every 10 seconds. If I was able to not do it once every 10 seconds, but instead 10 times faster than that, as far as the frequency of throwing it, let's say I wasn't throwing one 5 kilogram bowling ball every 10 seconds at 10 meters per second. Let's say I was throwing it 1 kilogram bowling ball, not once every 10 seconds, but once every 1 second. Everything else the same. Well, I'm throwing 10 times more mass in a given period of time. I used to throw 5 kilograms in 10 seconds. Now I'm throwing 5 kilograms every second. That means for every 10 seconds, that's 50 kilograms. 50 kilograms is 10 times more mass than 5 kilograms. It's going to be more propulsion. It's going to manifest itself as greater thrust when I'm throwing that. And that's kind of the whole premise of what's going on here. It's essentially Newton's third law. It's action-reaction, that's for sure. It's Newton's third law, and that's also manifested in the fact that it's conservation of momentum. So Newton's third law goes hand in hand. Newton's third law goes hand in hand with conservation of momentum. Pretty fascinating in that regard. Well, the rocket is standing still, and there's a lot of, there's as you can see, I have 2 books, maybe you can see these, I think you can see them. I got 2 books in front of me. One's calc-based and one's non-calc-based. The non-calc-based book, in my opinion, the Serway book, is a little more intuitive than Dr. Katz's brilliant presentation. Dr. Katz also gives a brilliant presentation, but I just think it's a lot more attainable, I think. It's a lot more common sense comprehension for people. When you look at the non-calculus look at what they're trying to say here. There's a lot can be said, guys. Let's try to say a good amount of what can be said. The rocket's there, it's not moving, everything fires out, and there's a lot of intricacies we can look at. Let me just give you the basics for us to be able to get this thing under control. In the Serway book, they're saying that, okay, let's say there's, they're saying a lot of stuff here. So you could say the rocket's at rest, or you could say that the rocket's already moving with a particular amount of momentum already. Let's say the rocket's either at rest or it's going at a constant speed. Either one will work. Okay, so in the Serway book, they kind of say, at a given period of time, let's say there is motion. It's not a big deal to say that there is motion, you guys. Let's say that at a given period of time, there's a lot of ways to write it, but let me kind of be faithful to how Serway's writing it. But there's certainly a number of ways this can all be written, guys. There is the mass of the rocket. Now, what's the mass of the rocket? Well, the mass of the rocket is all the stuff that's in the rocket, including the fuel. And the one thing about the mass of the rocket is the rocket keeps getting lighter and lighter. There's a certain point beyond which the rocket's not going to get any lighter. But when all the fuel is exhausted, the rocket's as light as it's going to be. And it's as heavy as it's going to be when all the fuel is in there. So basically they're saying here, guys, let's say there's a rocket and it's got a mass M. This big mass M has fuel in it and it has a lot of other stuff in it. And let's just take some of that fuel from M. There's like the whole rocket has M, which has got everything in there, all the equipment, everything, the people, all the equipment, everything else, and the fuel. And then I'm going to take some of that fuel, and I'll say that, okay, at least some of that fuel is eventually going to get thrown out of there. So it's going to be this. So for an instant, delta small m plus capital M is all the mass that's in the rocket at a particular time when the rocket happens to be moving at speed v. Well, what happens is when delta M gets expelled from the back part of the rocket's going to propel forward and go faster. So it's not going to have capital M plus delta M. It's only going to have capital M. It's not going to have capital M plus delta M after you expel delta M. It's only going to have capital M. Yeah, but it's going to be going V plus delta V. It's going to be going a little bit faster. And the delta M being expelled, the small delta M being expelled, now here we got to be careful. What's going on here? Momentum is momentum, and momentum is conserved. This is all in one direction, so to speak, when it's loaded up very, very much. Then delta M gets expelled, and you only got big M. Here you got big M plus delta M for everybody at a particular time going at a speed V. When delta M gets expelled, you only got big M. You don't have big M plus delta M anymore. You just got big M. Yeah, delta M got expelled, but you sped up because you expelled the delta M. Yeah, the delta M got expelled, but it got expelled out the back end. So it's got a negative velocity, negative V sub E. Now they write it, Serway writes it V sub small e. I think what I've been showing everybody, I put V sub big E. That's not a big deal. Whether it's V sub small e or V sub big E, we're talking about exhaust. Here's the big thing where you got to kind of watch out. It is a negative V sub E. Why? Because it's a vector quantity. This guy's positive. He's going to your right. He's positive. He's going to your right. He's positive. Yeah, and so is this guy going to your right. This guy's going to your left at negative VE. Not so fast. Not so fast. That delta M gets expelled from the rocket relative to the rocket at a magnitude speed of V sub E. We say negative V sub E because it goes out the back end while the rocket's going forward. The rocket's going forward and the other thing's going out the back end. It's going out the back end at V sub E relative to the rocket. But relative to some stationary object in space that doesn't move, let's say the Earth didn't move at all, relative to looking at the Earth, this thing is going at V sub E, negative V sub E, not really because he's being carried away at V. So it's V plus a negative V, V plus a negative V sub E. It's got to be V because that's the momentum vis-a-vis the Earth. You know, let's say the Earth was stationary completely. Okay. Well, you look at something like this, you guys. You look at something like this, and you know, Serway does some pretty fascinating stuff. But so let's look at it. Let's go right here. We go mv plus delta m v mv plus m delta v plus delta m v minus delta m VE. Let's subtract capital MV. Let's subtract capital MV on each side. Let's subtract delta MV on each side. And what we got is 0 equals M delta V minus or plus or whatever you want to call it. It's not a big deal. Trying to see how I want to write this. You look at this right here. It's not a real big move for me to just say M delta V, leave it like that. Add a positive delta M, add VE delta M. VE is a constant. Now, this is pretty interesting. There's a lot that can get done here, and it's not going to. Sometimes the signs play a role, sometimes they don't. The increased delta M in the mass of the exhaust corresponds to an equal decrease in the mass of the rocket. So delta M is negative delta M. So the increased delta small m in the mass of the exhaust corresponds to an equal decrease in the mass of the rocket. So delta small m is negative delta m. Using this fact we have. So not the biggest deal in the world, but to speak that language, they're saying basically this delta M increase in exhaust, this is a positive number. That's negative delta big M. That's negative delta, because delta big M is a negative number. So negative of a negative number gets you there. So they end up doing this. And there's a lot you can do here. You can write the delta V here, divide by M, delta big M, divided by this. This is true. We're not done, but this is true. Man, there's a whole lot you can say. Make sure I did the right. I don't think I did the right thing. Yeah, right. There was a negative right here, guys. Forgive me. Negative here, negative here, and this kind of ensures the negatives don't play a role in terms of magnitude. Even when you get into the logarithmic function, when you're trying to describe a lot of what's going on with this, it's no big deal. The logarithm of a ratio is equal to the negative of the logarithm of its multiplicative inverse. Give an example. We're gonna see this in a little bit. Just kind of keep this in the back of your mind. ln of x over y, that's the same as ln of y over x. Just throw a negative in front of it. So you'll see the magnitudes don't differ. Now, why is there a negative here? Because you got to remember the rocket is being propelled in one direction. Right, and the exhaust is being propelled in the exact opposite direction. Call one of the directions positive and call the other direction negative. Call the rocket's direction, call that positive. Call the direction of the exhaust, where that's going, call that negative. So that's kind of where this is coming from, guys. This right here, delta M is a negative number. So it'll come out. There's a lot of ways you can do this. You almost don't have to do what Serway was saying. Just pretty fascinating stuff, though. Really fascinating the way they describe some of this stuff. Now, this delta V is, there's a lot happening. So for those of you, I don't know where to start, where to finish on this. Let me write this down, and this will apply both for the calc version of mechanics and non-calc version of mechanics that can be talked about. There are, let me try, yeah, I think it's fine. I'll use what Serway said. It's almost more straightforward. As long as you're okay with the language, you should be all right. Let me leave this alone for a second, and let's do something with this when it's time to do something. Negative, so delta M is a negative number. Delta M is negative. Negative times negative is positive. Positive change in velocity. That makes sense. The rocket is going to gain velocity. Okay. And there's a number of ways this looks. And again, Dr. Katz's look at this is very brilliant. It is very rigorous, and it's very useful. Serway's look is, to me, a lot more straightforward when you're first looking at something like this. And there's a number of things you can do, even with the calc version of what's going on. All the games you can play, guys, with this stuff. So because kind of say this, I guess I have a number of things written down pretty soon. You're going to draw a conclusion where the change in velocity, this is big, that's small. That's usually the way it is. It doesn't have to be that way. You could be putting the brakes on too. You could be using the rocket to brake, to slow things down. But let's say this is big, let's say that's small. VF minus VI equals, and this is a little, again, Serway uses, I got at some point, I'm trying to unify the two books, guys, so I'm going to have to, at least I feel like it's okay for me to use a capital E there. They use small e, it means capital E and small e mean the same thing. So VF minus VI equals VE ln MI over MF. Mass initial is bigger than mass final. Mass final, fuel has been burnt. It's a smaller number. The logarithm, this is a bigger number. Initially, there's more mass in the rocket because there's more fuel in the rocket. Less fuel in the rocket means, less mass. There's a lot of fuel in the rocket. M sub I, the initial mass, for some initial consideration, is a big mass compared to a smaller mass when the mass of the fuel, a certain mass of fuel has been expelled. So MI is big, MF is small. Big divided by small is a number bigger than 1. ln of a number bigger than 1 is a positive answer. A positive answer times VE will tell you the difference. They got this thing called thrust. They write it differently than what I'm going to write, but I'm just going to say force thrust, instantaneous thrust. Instantaneous thrust is the instantaneous mass times the instantaneous acceleration at that moment. That is m delta V over delta T. And that, well, here, this is kind of interesting. Come back with me. Let me, we can go anywhere you want. Actually, with this, let me try to speak their language. Let's go right here for a second. Why don't you divide by delta T on each side? And you got m delta V over delta T equals negative VE, right? Let me see here, right. I'm taking this one into consideration, guys, right here. Let me take this one for now. And then later on, I'll talk about this one. So let's talk about the red right now, and we'll bring the green in later. Divide the red one by delta T on each side, and you got negative VE delta M over delta T. Wait a minute. Isn't this mass times acceleration? Delta V over delta T. Delta V over delta T is acceleration. Mass times acceleration is force. This is also equal to the same force, which is equal in this case to negative VE delta M over delta T. And that's all they're doing here. And they kind of, because there's a negative there, guys, because there's a negative, they put absolute value symbols there. And they put VE delta M over delta T. So that's a lot of that Serway. It's great as far as I'm concerned. Let's kind of just say something here, get it there, and then kind of just translate it into some of the vector notation that's pretty good also. So you look at this and say, okay, well, whatever, you're saying all this stuff, great. Let's go to the green one. You saw what I did here, right? Saw what I did here. And, basically, I mean, they're the same thing. I just didn't, here I took this equation and divided by big M on each side. I took this equation and took this equation divided by big M on each side. I got to here. All right, now, let's look at the green one. Not much of a difference here, guys. Let's use, those of you who have a calculus background, please pay attention to this. If you don't have a calculus background, don't worry about it too much. Just, I mean, like if you're in a calculus-based class, please pay attention to it. If you have the calculus background to begin with, not bad to have under our belts. This delta V, it becomes a calculus problem when you convert the deltas to D's. The delta V, I'm going to make into dV. I'm going to make this guy d big M over big M here. VE is a constant. I am going to take this guy and integrate it from VI to VF. This negative VE is a constant. I will pull that out of there, and I'm going to integrate this guy from MI to MF dm over big M. This integral gives you V evaluated between the limits of VF and VI. In plain English, it's this. If you're in the non-calc version right now, don't sweat it too much. This one right here is VE. This integral right here is ln M. ln M evaluated between M sub F and M sub I. And it becomes ln, well, it becomes a lot of stuff. It becomes, in the end, it comes this. What happens is when you evaluate MF, MI, it's ln MF minus ln MI, which is equal to ln So it's that. By the way, that's a negative number. MF is a small number compared to MI. Small number divided by big number. Number smaller than MI divided by MI is a fraction less than 1. The natural logarithm of a fraction, less than 1. This MF is a small number, this is a big number. This MF is smaller than MI. Smaller than MI divided by MI is a fraction less than 1, decimal less than 1. Fraction less than 1. ln of a fraction less than 1 is a negative number. Negative number, VE is positive, but here's a negative put right here. Negative number times a negative number is a positive answer. It'll work. It'll work just fine. It's also the same as this. Negative ln MI over MF. What does that mean? Well, that means it becomes VF minus VI equals negative VE times negative MI over MF. Negative times, well, negative times negative is positive. It's VE ln MI over MF. VE ln MI over MF, or you could write it as negative VE. You could write it as VE ln of the quantity MI over MF, or you can write it as negative VE times ln MF over MI. It means the same thing. So that's kind of where the stuff, that's where it's coming from when you do that. Let me see, guys. See what else I could say here. Kind of going. I don't like erasing any of this stuff sometimes, but you guys also have it. You guys have all of this. So there's a lot we can do here. Remember now how logarithms work. The natural logarithm of a fraction is equal to negative the natural logarithm of the reciprocal of the fraction. And that's where we can get, that's where we can play a lot of games with the signs, you guys. which can sometimes make a big issue. So, kind of ends the story right there. You know, kind of a more rigorous look at it. Not much of a, I mean, there's different ways, so many different ways to look at this thing actually, guys, but let me kind of use Dr. Katz's notation just for anybody who wants to look at it that way. The way up there, upper left-hand corner, the VF minus VI, the VF minus VI is delta VR, the change in velocity of the rocket, change in velocity of the rocket, change in the change in the velocity vector, the change in the velocity vector of the rocket. And like I said, Dr. Katz goes into it pretty strong. This is VE, and this is VE in regard to the rocket. And she writes it, the rocket final mass, which is a small number, compared to the rocket's initial mass, which is a big number. She goes into the thrust here, talks about, notice how, you know, she's really rigorous about the actual vector quantity here. VE R, and this is more again calc based, big time right here, calc based. For the guys doing the non-calc version of the class, you guys, these D's are deltas. These D's are deltas. Delta MR, delta T. But this is D right here. Don't lose a tremendous amount of sleep on this stuff, but it is rather interesting. Notice the VE, the velocity of the exhaust, is the velocity of the exhaust with regard to the rocket. Let me kind of see here. I don't know if they actually get into that. They don't really get into that. VE is how fast it's expelled from the rocket, vis-a-vis looking at the rocket. So they're going to get, in other words, you're kind of treating instantaneously as though, okay, here's the rocket. You're sort of just saying, okay, just by virtue of the rocket, how fast this thing moving away from the rocket. Pretty fast. I mean, very fast. How fast is this vis-a-vis the Earth? Let's say the Earth, for some reason, we'll just say, okay, we'll take the Earth as completely stationary, or some object in the universe or something. You look at, okay, here it is. There's some object. Let's say it's not moving at all. Relative to that, what's going on here? Let's say there's no motion or something. Just for the sake of the mathematics, if for no other reason. How fast is it going? Well, you know, it's negative VE if it's standing still. It's not as much VE if it's being carried along. So it's what's coming out of the rocket. VE is what's coming out of the rocket. V minus VE is the velocity relative to the Earth. VE is relative to the rocket. V of the exhaust relative to the rocket is VE. Relative to the rocket, it's this. Relative to like a stationary Earth, or actually it's negative this, it's going in a direction, in a vector sense, opposite to what the rocket itself is going. So it's negative VE. Well, yeah, it's just not as big a magnitude. This is a big magnitude. If the rocket is completely standing still and the stuff's just firing out, or just in relation to the rocket itself, that's a big magnitude. This is not as big a number because this is negative. This magnitude is big. It's as big as this magnitude, but this cuts down on the magnitude. The fact that you're carrying it with you relative to the Earth, that's what the exhaust is doing. That's what we did earlier. This is what the exhaust is. And this is what it's doing relative to the rocket. And that's what Dr. Katz is saying in various places here, guys. So largely the Serway book here, largely the Serway book there, and largely the Katz book here. And you saw some of the calculus that got you there. The rest is, from the calc version, do you have this under control in the calc version? In the calc version, do you have this under control? A lot of what goes on in the calculus version of courses like this can be handled here pretty darn well. A lot of what goes on, even in the calculus versions of the course, can be handled here very well. Oftentimes can be handled quite well right here. And for the non-calculus versions of the course, obviously then this is where you're going to go. But even with the calc version of the course, you can go into here and get a lot out of this. And in the non-calc version, go here as well. But can you manipulate this? Do you know how this stuff works? What is the inverse? What is the inverse of the logarithmic function? It's the exponential function. The inverse of the natural logarithm is the exponentiation base e. E to the x and ln x are inverse functions of one another. So if I want to solve something and not have logarithms present, I have to exponentiate both sides. I have to set up the equation in such a way and exponentiate both sides. All right, guys. Thank you for your time. Take care.